Okay, so we are live on YouTube. And I suppose we should start. So I don't know if the length scared off some of the people from yesterday, but people have been watching on YouTube also, so it's fine. Okay, so I guess we can start.
Okay.
So, Massimiliano.
So so we are in. So welcome everybody. Thank you for being around. So this is lecture 2. So the first lecture, not very much went on, okay, but again, I stress again that there is a message which I want to make with this 3 lecture, which I feel is still not passed around, at least not many. When I interact with people, I don't feel it. I mean, for me, it's an important point that sometimes it's strange that people do not that they see, but they acknowledge that this point of view exists. Okay, so let me try to stress it. So my point for today, I prepared the lecture with a goal. So let me just, what we did yesterday, okay, we introduced these concepts of Euclidean quantum field. I told you I want random field which have 3 properties, Euclidean covariance. So when you translate the random field, it's the same law everywhere. And reflection positivity, which is this strange property, and it's needed for other reason. We are not concerned very much about the reason, but the consequences are that Euclidean invariance and reflection positivity essentially force us to try to construct this measure in a very specific way, which is full of difficulty. There are 2 kinds of difficulties. There is the need to take an infinite volume limit and need to take a small scale limit, and both are quite tricky, could be quite tricky. And actually, when this problem was framed in a mathematical rigorous way, a lot of very interesting mathematics came out from that problem. Okay, in the 70s, 80s, Glim, Jaffe, and many other people contributed very interesting mathematics on this subject. Okay. And then I told you I wanted to do this, look at this problem in a new, different way, if you want. It's not very new, but it's relatively new. And that's because somehow a very interesting model could be only addressed very recently. But this came as a surprise, if you want. And thinking about why somehow there have been this surprise, why somehow, for example, doing stochastic quantization, I mean, we found new proof for all theorems, if you want, let me say in this way. And this came somehow as a small surprise, even to me or to people in this field. And thinking about why, where this surprise came from, I tried to conceptualize what's going on in the sense of saying that what we are really trying to do is a stochastic analysis of Euclidean quantum fields. Okay, so, and then I try to motivate what I mean by stochastic analysis and what are the analogy you have to keep in mind. I will not go back to this. Essentially, you have to keep in mind that every time you want to do an analysis, you have to have a basic building block, and you have a way to analyze, to look at the building block inside a more complex situation, and then to synthesize the more complex situation out of your simple building block. Okay, that's the kind of movement you need to be able to do. And just to free your mind from some preconception, I also make a list of various ways you could have a stochastic analysis of Euclidean quantum field, which I call briefly and maybe not very precisely just stochastic quantization. Okay. So for me, stochastic quantization is a term which is stochastic, which just resumed this idea of having a stochastic analysis of Euclidean quantum field. And this has consequences in the way you approach the problem and in the kind of problem you want to look at and how you want to solve them. Okay, it's it's a mathematical concept, but it has mathematical consequences. And I will try to exemplify today them in try to make to prove some things, okay? And I want to prove how you take the infinite volume limit for some kind of measure I introduced the last time, and how we renormalize the measure. So try to take the small scale limit, at least I will try. Otherwise, we continue on Friday on that. And then on Friday, I will certainly want to speak about properties of stochastically quantized measure, okay? How you prove properties of these measures, and maybe elliptic stochastic quantization, but let's see. So I will not go back again in the setting. I just, because I need very vaguely various objects. So I remind you that I'm just to simplify and to make things quite elementary. We look at a bounded box. The size of the box is L. Inside the box, you have points, a distance epsilon, which make a lattice, okay? So in the dimension. So this will be lambda epsilon L, and sometimes I don't write epsilon L if they don't move, okay? But you have to keep in mind, if you feel confused, please ask questions, okay? Sometimes I just don't write all the indexes. And then what we did the last time is that I tried to motivate you the idea that I want to study this family of measures for the reason I explained the first lecture. And this family of measures are just Gibbs measures, which are given as exponential as Gibbsian perturbation of the Gaussian free field. So mu is the Gaussian measure with covariance, the inverse of this operator A. Okay, so Gaussian, if you want, so this is the Gaussian measure with mean 0 and covariance given by A minus 1, okay? Of course, you are on the torus, so the measure depends on the lattice spacing and on the lattice size. And then you want to perturb them, and I recall to you that this function, sorry, actually, let me write, so because V in the following will be really the integral. So this is really the sum, it's not an integral because you are in a finite domain. So it's something like this. So the sum over all the lattice point of this, of a polynomial function. Let's say we took a fourth order polynomial. Okay. So something like this. This was like lambda, and then c to the 4. Let's fix to this model and b depend on epsilon. Okay, it's a constant to the square. Okay, so this was our model, and I introduced a dynamics which has this as invariant measure. Okay, so it's a dynamic for a finite number of degrees of freedom. So time is continuous, but space is discrete. And the dynamic is a drift, so it's an SDE. You have Brownian motion in every lattice site. They are all independent. And then you have a drift, which is linear with coefficient A. So A is the discrete, is just a matrix, okay, because you are in a discrete setting here. And then you have the pointwise evaluation of the potential. Okay, if I write the coordinates, here you will have something like this. This is a matrix, so it's not diagonal, but everything else is diagonal. Okay, let me remove this. I don't need, and maybe X is a point in the lattice. Okay, so this is my setting, and I claim that, okay, this is, of course, you have to prove it, but essentially it's well known that this is actually in this setting, the only invariant measure for this dynamics, okay? Then I motivated that I wanted a building block, and in this context somehow, and even for the later, the natural building block, as far as I see, okay, it's not dictated by anything else but simplicity, is to take the solution of the linear equation. Okay, so I ignore the perturbation, and I solve the linear equation. That's easy, give us a Gaussian process. So why it's a Gaussian process? Because it's solution of a linear equation driven by a bunch of Brownian motion. And it has, as you can check, it has an invariant measure, which is the Gaussian free field. Okay, so I will call Y the Gaussian free field. Okay, it's the dynamic, if you want, the dynamic Gaussian free field, if you want, or the Oster-Uhlenbeck process is a kind of Oster-Uhlenbeck process. But the point is that now I want to use this object as to do my stochastic analysis. Okay, this will be my building block, and I want to construct or study the solution of the full dynamics in terms of the solution of the linear dynamics. Okay, not because they are nearby, but because somehow you look at locally, they looks very much similar. Okay. And also in some sense, also in a global sense. And then in order to do so, I changed somehow, instead of looking at X and Y, so X is the full solution, Y is the solution of the linear equation, I change my variable, I look at Y, and then I look just the difference from X and Y, and I call it Z, and Z is a process which satisfy a random differential equation. Okay, there is no Brownian motion anymore. So you see this equation, I have to write it in somehow in the Ito sense, understood as an integral equation. But the equation for Z is a good old ordinary differential equation, and the only randomness comes in Y in this equation. And again, I stress that Y is a Gaussian process. Okay, so you give me Y, which is a Gaussian process. I solve this equation, I find Z, and then I can reconstruct X. So no information is lost. And I have a very easy machinery in some sense, a very classical machinery to construct X from Z, just solving an ordinary differential equation with the randomness inside, but that's not very important. Okay, you give me a sample of Y and I can solve this equation pathwise, okay, sample by sample. There is no probability involved in solving this equation. Okay, that's an important point for me because it makes you already a splitting of your problem. When dealing with the equation, we essentially use only analytics tool, so no probability. And then in the equation, you have coefficient depending on Y, and Y it's a random object, and then you have to use probability to understand this random object. Okay, that's give you a splitting, nice splitting of your problem. And again, okay, I wrote down what is V prime, I wrote what is Z, and now the basic tool I want to explain to you how you deal with this equation. First, it's an equation with non-Lipschitz coefficient, so it could explode. So we have to care that it does not lead to explosion because you see it's not, the coefficients are not globally Lipschitz. And somehow the idea will be used later on also to prove some estimates. So what is a basic idea could be, okay, I just multiply the equation with Z. This is basic reflexing for an analyst. Okay, when you want to study solution, you try to find estimates and a priori estimates. So you assume you have a solution, or you have an approximation of the solution, whatever, or you stop before the solution explodes because it could explode. And you write down something like this. That is, you compute the derivative of some function of the solution. Here you took the square, and then which correspond to just multiplying the solution with Z. Okay, I multiply with Z here, and I multiply with Z there on the right-hand side, and you rearrange your terms, and you obtain a formula like this. Okay, because Z times the derivative gives you the derivative of Z squared times 1/2, and then the other terms produce various contributions, which I grouped in two parts. Okay, there are the good terms, which I call it G, which are essentially all the terms which have a sign, which are positive when you put on the left-hand side, and they include the gradient squared of phi, which come from the formula for the Laplacian, essentially when you and the mass. Okay, so this is essentially the term G is just the scalar product if you want. Okay, you have let me not write maybe. So this term, they just come from this part and from the part where you have the cube. So you see here you have a cube in V prime, and then at some point you apply this to y plus z, so you have the cube of z, and when you multiply with z, you get the fourth power. And you get the fourth power with the right sign, because remember lambda is always positive. Okay, and then you regrouped here the group terms, and on the right hand side there are all the terms which do not have a sign, or which are not very they don't have a sign. Okay, because I'm not stipulating that beta has to be negative or positive. Actually it will be positive, but it's on the wrong side. When you put on the left hand side, become negative. So you see here all the other terms. Okay, now the game you want to play in order to have a priori estimate is that you want to use the good terms, which are the terms which I put on the left hand side, to estimate the bad terms on the right hand side. Okay, and you have two kind of good terms. The first kind of good terms is this one, because somehow if on the right hand side you make appear this quantity, then you can use Gromwall lemma, which is not very interesting for us in the context I want to talk about. But this term, it's more interesting. Okay, this term give you, somehow it's a term which you can make appear on the right hand side and then reabsorb on the left hand side. So let's see, how does it work? Okay, so now the goal is how I can estimate the term on the right hand side. Okay, because the term on the left hand side are good. This is positive, and this is the derivative of something. Okay, so the derivative, it's okay, and the term positive, it's okay. And yeah, I didn't wrote down but okay, let me just mention it briefly. There will be many times I will use the kind of reasoning, but you see, this is like a product, an L1 norm of this product, and then you can use Holder inequality to bound it by what? By the L4 norm of y and L4 norm of z, for example. Okay, and here the same, and here the same. So actually everything here can be bounded by the product of the L4 norm with the right powers, but then you can use Young inequality to bound them to just make appear make appear something like this. Okay, that is the L4 norm of y with a constant which is arbitrarily large, but you don't care. What is important is that somehow you need to have the L4 norm of, so this estimate is essentially, let me check. Yeah, for the fourth order term, you can use the L4 norm. For this term, you can use the L2 norm. So that's that's a bit different, but if we forget about that, you really use this L4 norm, which is here. Okay, and you can do this estimate, and you can check that for any delta small, you can bound this object in this way, or maybe I think you would need also the L2 norm, but that's not very important. So let me ignore it later on. The important thing is that the dependence on Z can be just bounded by small constant times this good term you have here. Okay, you need a small constant because you want to absorb. Okay, then again, okay, if delta is less than 1/2, then you can put this on the left-hand side, and this is still a positive sign. So you have an inequality, you integrate your inequality, and you have something like this, okay, with maybe some other terms. Okay, let me be consistent with what I wrote, so something like this. Okay, and the constant C depend on delta, but you don't care, you choose delta 1/2. Okay. So that's a standard tool. I'm not claiming anything crazy, just introducing the kind of idea I want to use. But that will bring us a lot already. Okay, but we still have a problem, okay? Because you see this derivative, when you integrate, it gives you, of course, the two boundary terms. So give you the solution at time z and give you the solution at time 0. So solution at time z is in the left-hand side of the inequality. So you can drop it, you don't care. the interesting part is this one, as you will see. But this is a problem for us, is in the right-hand side. And it's somehow something you don't know, because you see Z0 is the initial condition of your equation, and you can choose it. So somehow you can, sorry, you cannot choose it, because if you think what you are doing, somehow what you want to do is that you want to use the dynamics in a stationary setting. So somehow you don't know very much about Z0, and you have to, Z0 is given, is like X0 minus Y0. And X0 you cannot choose, because somehow it's just sample from the invariant measure we want to study. Okay, so this is somehow part of the problem. You want to study an object, which is this measure nu, via the dynamics, but somehow the unknown, the measure nu, which you want to handle, appears many times. One of the time is here, because somehow this time you don't know very much, because it would imply that you know already many things about the measure. Of course, we know the measure, but I don't want to use it. Okay, I don't want to use the explicit form of the measure. My goal is just to use the equation in order to get my theorems. Okay, so that's the game I want to play. So how I close this estimate, since I don't know this term, and there are various ways to do that. So let me say pedagogically, I think the easiest way is to introduce a stationary coupling. So I want to couple Y and Z, so Y and Z as two stochastic processes, in such a way that the coupling is stationary. Okay, so again, okay, let me go back to make this point clear. You see that I claimed, and it's true, that X is a stationary process if you start from this measure, and Y is a stationary process if you start from this measure. So somehow, provided you start X with the measure nu and you start Y with the measure mu, then each of them is stationary, but somehow they are not independent, because they depend on the same noise. So as a joint, as a couple, as the couple XY as a process is not stationary anymore. And you want a coupling of these two, which is stationary. Okay, so that's the problem I want to solve. Okay, and the coupling is not the independent coupling, so you cannot just take the product of these two measures. Okay. And the idea what it is, well, you start with the product of the two measures. So let's construct the dynamic with the product, and then you just use a Krylov-Bogolyubov argument. So what does it mean? Well, you introduce a new measure in the product, which is just somehow the average of the empirical mean over the trajectory of the coupled process. Okay, so the coupled process, the two processes together is not stationary, but you take this empirical mean, and then you take an average over the law of the process. And then you know two things. Well, if you look at the sum of X and Y, that this is X, but X is stationary. So you see this particular marginal of this measure, it's nu. Okay, so the law of the sum of the coordinate under the measure nu t, it's nu, it's independent of t, this interval of time t. That's good. Of course, and the law of, again, the law of y, it's mu, okay? And similarly, let me record this, that if you take, f is just a generic function, okay? So let me note the same thing. If you just look at the first component, which is y, okay, so this is just the average of y, and you can repeat the same argument, okay? So this is just average of y, but y is stationary. So this is just y0 and y0, so you have mu here, okay? So somehow this measure has the right marginal for these two functional. Good. And so now I want to take somehow, this is standard in Krylov-Bogolyubov. If this family of measure has a limit, then the limit is stationary for the dynamics, okay? Because it's the way we constructed it. So we need somehow some tightness for this family of measures in this parameter t, which I introduced. And now we use the a priori estimate. Okay, so we integrate the function g, which control the second coordinate, and just one norm of the first coordinate, which I choose so that I can close the argument. And so what does it mean? Well, I use the definition of gamma, which is, this is just the average of the empirical mean of G computed on Z and the norm of Y. And then we use, I remind you, so this is probabilistic, but then we use the analytic input, okay? The analytic input says that this integral in time is less than all this stuff, okay? And I can drop the initial condition if you want. So I have 1 over t, and then using the bound, I have something like this. Okay, so I have 1 over t time this quantity, but this quantity I can estimate in terms of x and y, so that's not a problem. And I have that. Okay, so that's not a problem so far. Okay, so and this implies somehow, then one can check that this is uniformly bounded in T. Okay, one could even remove this dependence. That's not very important right away. Okay, so for the moment, I'm concerned just with the T, the tightness in the parameter T. Okay, but you see that the right-hand side does not depend on T. Okay, can be bounded uniformly in T. So this gives you, this is a coercive functional. And then you have tightness for this family, okay? And then you compute the limit and you have a coupling, okay? So this is a coupling of Y and Z, which is stationary under the dynamics, under the joint dynamics, okay? So this is a technical step. It can be avoided with other techniques, but I think it's nice to see. Okay, so right now, so what we have achieved, we have a way to start the dynamics of Z and Y in such a way that it's stationary. And I have to start it by taking the initial condition given by any accumulation point. Okay, I'm not claiming any uniqueness, it's tightness argument. So you have an accumulation point, any accumulation point is stationary. I just need a stationary measure coupling, okay? And now I want to use this stationary coupling to say something interesting. And the first thing, the easiest thing I can look at is the infinite volume limit. Okay, so I want to keep epsilon fixed. So lattice is fixed and taking infinite volume limit. And the idea is somehow, like in statistical mechanics, you have to localize your observables, okay? Because of course you cannot look at the full lattice. In order to see convergence, you just have local convergence, okay? Convergence for local functionals, and you can implement these very easily by using weight, a weight, okay? So weight for me is just a function which decreases to infinity and which localize my norms, okay? My norms do not take into account the full space because the space is becoming larger and larger. It's just taking into account a finite portion of the space, okay? You could take other norms, okay? You can take norms which are compactly supported, but this gives you technical problem later on. So this kind of polynomial decreasing norm, so sigma is just a positive number, okay? And L is also a positive number. These are just parameters you have to choose at some point to get something work, okay? It's not, let's say L it's large enough and sigma it's large enough, that would work. And then you repeat the same argument, but now you don't look at Z squared as before, but you multiply also with rho. Okay, technically what you do, well, you look at the equation for Z and you multiply with rho squared Z, and then you sum over the full lattice, okay? And you integrate by part the Laplacian. And the form of the weight enters in the integration by parts of the Laplacian, okay? And this generates all the terms you already know with the weight, and also you see the 4 power with the weight, which is 1/2 if you think what happens, because somehow you multiply with Z squared, but the L4 norm has a 4 power, so you have to take the square root here. And this is squared because it's in the L2 norm, this is squared also. And here you have to integrate by part the Laplacian to make appear this positive quadratic form. And when you integrate by part the Laplacian and you and you use the explicit form with the weight, you can essentially bound some correction term by this kind of term. Okay, these appear because you integrate by part the Laplacian. It also means you cannot take any weight. Okay, so the constraint on the weight come essentially from the interaction with the Laplacian and from the integration by part. But essentially, the structure of the computation is the same. You have good terms. You have this derivative, which we will not use, and you have the bad terms, which you will bound by Young's inequality, okay, Holder and Young inequality as before. So you get a similar estimate. I'm going a bit fast, but this is exactly as in the unweighted case. So you see the terms you don't know are on the left-hand side, most of them or some of them you can reabsorb, and the terms that you do know, like norms of y, because again, okay, you have to keep in mind that z is the unknown, the things you want to analyze and get estimates and information, and y is the Gaussian process, is the thing that you know probabilistically very well. Okay, so what I'm doing is always use analytic argument to get estimate on z based on y, and that's good. Okay, so this term can be put on the left-hand side. Very good. The interaction term, you see that you have to be careful with the weight. You have to split it in such a way that you can reabsorb. But essentially, the idea you see here, the idea is that you split the weight, part with y and part with z, and then you use Young and Holder inequality to make appear the L4 norm of y. To make appear the L4 norm of z, because this is what it's in G with the right weight, which is 1/2, and these make appear also corresponding L4 norm for y. And then, okay, so this is inside G. You see, you have to take care about lambda, because I don't want to have dependence on lambda around, and lambda can be very small. Okay, so particular, the L4 norm of z has to be together with lambda, and you have to care about that also in estimates. And delta can be chosen small, but 1/2 in this case, it's okay, or smaller in some other situation. That's not very important. The important point is that at the end, you get a similar estimate, but now with a weight, which is decreasing, okay? So keep in mind that you are summing over the full lattice. The lattice you want to make to go to infinity, so this causes a problem. But you have this weight, which is going to 0, so it helps you with the convergence of these norms. Okay, and now, so this is the bound, and now I'm exploiting, so how I get tightness. Again, I have always the same problem, okay? I have this term on the right-hand side is not very good because I cannot control it, especially in the infinite volume limit. Okay, for the tightness argument, it was enough that it was finite, so I didn't have to say very much about it, but if you want to take the infinite volume limit, you need to prove that the expectation of this term it's bounded, and that's not what you want to do. So you want to get rid of this term. And again, if you use the stationary coupling, now z is the difference of two stationary processes, so it's stationary. So you have the average is the same, and then it disappear from the bound, and the bound you can write also in this way. Since the coupling is stationary, the difference again is stationary, so you can write this expectation as averaged along the trajectory. When you have t positive, then you can use the a priori bound from the equation, which you see convert this bound on this functional of z into a bound of a functional of y. Okay, so this is where the stochastic quantization equation make its usefulness, in the sense that you are estimating a quantity which you don't know very well with a quantity which you know very well. And then on top of that, y it's a stationary process, so you just go back to estimate on the Gaussian free field, okay? Because remember that under the stationary coupling, Y0 is distributed as the Gaussian free field. Okay, and again, okay, I made this computation, and essentially the idea is that since you have the weight, and since, okay, I made just an explicit computation to make you see what's going on. Well, you exchange expectation with the sum, and then this is a stationary process. So whenever you compute, this average is the same. So you just get a constant, and then the sum over x is taken care of by the weight. Okay, so if the weight goes to 0 fast enough, then the sum it's finite, whatever the size of the lattice. Okay, because you can take the infinite volume here in the estimation. Okay, so this estimate it's uniform in L. And this give us tightness, okay, because this tells you that this quantity is uniformly bounded in L. Okay, and yeah, and so let's see if I said something. Yeah, so let me write it here. So what is this exactly? So remember that our coupling was such that when you integrate with respect to the difference, then you get really the integral with respect to the measure. So what are we really estimating is this quantity, okay? So what we have, if I have to write it down, what we have obtained is that this supremum is uniformly bounded, okay? And since the function g is coercive, yeah, well, G depend on rho, sorry, in this case. So let me be more precise, okay? So G contains, for example, contains, if you want, let's go back. So what contains G? Yeah, it contains all this contribution, okay? So let's take only one of them. For example, let me take, I don't know, one of these two, it would be enough for convergence. Let me take this one, okay? But again, okay, you don't, so I could write something like this, okay? So that the supremum is less than 1 over L, which is bounded, okay? Uniformly in L, okay? And this give you tightness. You have to work a bit to set up things in such a way that you can claim that, but essentially this tells you that locally, so phi, so you see this localized in space. So you're looking at the local fluctuation, sorry, of psi or phi, whatever. Let's write in this way. And you're looking at the local fluctuation of the field. And yeah, sorry, here there will be Z, but yeah, let me. Yeah, because there is also Z, but essentially you can split the two and prove something like this. Okay, just yeah, this is not exactly, this is not precise because actually it's not only Z that you're estimating. So let me just state briefly in this way. Let me see how I can adjust this. So yeah, so this supremum. So yeah, one way to say is that, okay, this is, yeah, okay, let me be vague because I don't want to, I mean, from this estimate, it's clear that, namely from this estimate, one can deduce, yeah, now I can deduce that, okay, so that this supremum is bounded, okay, and yeah, so this weight, it's arbitrary. You can center it wherever you like, okay, because somehow we only use the fact that it decays as a power, but not the fact that it's centered in 0. So you can center everywhere. So you have a family of semi-norms, and they give you tightness in the topology of local convergence, okay? So when you test with functions which are compactly supported. And working a bit, actually, this allows you to construct a stationary infinite volume limit for the Gaussian free field, which I will not explain, okay? But you say that's the point, okay? These uniform estimates are the key to get the tightness. And you see that the argument is not very complicated, okay? So we just use a PD argument and this stationary coupling. And then with the same ideas, you can elaborate this kind of idea, and then you can, instead of only the L4 norm, you can control higher order norms in the same way, and obtaining more or less the same kind of results. Okay, that is essentially any polynomial norm is bounded, and working a bit harder, you can also control non-polynomial exponential norms, but I will not enter very much. Maybe you can look at the paper with Martina to see how you do. But the idea is the same, okay? For polynomial norms of this exponential norm, you just test the equation with the right quantity to get an estimate, okay? To make these kind of norms appear and then estimating them, okay? It's not very complicated and is in the same, no new idea are needed. What's a new idea? So a different approach. So I use this stationary coupling. That's not necessary in general. There is another approach which has been used in other papers. Sorry, this is the new paper. So this is the second paper. We have two papers, Gubinelli of Manova. There are two papers, one 2020, where we use this coming down from infinity, and this is the second paper where we use this stationary approach. Okay, but another approach is essentially called coming down from infinity for this kind of equation, for equation of the 5-4 kind, polynomial with polynomial coercivity. And this was essentially discovered or pointed out by Murray and Weber. And Mona Weber gave a version with regulated structures. Okay, and what I want just to explain this in one slide, because I think it's an interesting thing to know and to keep in mind. Maybe it's useful for you another time. I found very amusing, and the idea I explain in one dimension, okay, because the idea it's already there. And then when you want to study a PDE instead of ODE, you have just to work a bit harder with the Laplacian, but nothing new happens. So think about the one-dimensional version of my problem. That is, I have a random, an equation where you have, I simplified, okay? I kept only the bare minimum, the time derivative, the third order polynomial with the right sign, and some additional terms which I don't care for the moment, okay? So you can put there anything else. And then the idea is, again, okay, to test this equation with a polynomial weight in the time variable, which is 0 at the origin. Okay, so now instead of looking at y, you look at rho t, yt. So rho t, yt is a function which starts from 0 because rho is 0 at the origin, and then grows or decrease, whatever, and you look at the maximum point of this function. Okay, let's assume that y is positive somewhere in the interval 0 t, because if it's not, you have already an upper bound, and lower bound can be under in the same way. Okay, so I just want to show you how to get an upper bound on the size of the solution of this equation. So you multiply, and then you assume that you have a maximum for this quantity somewhere, everything is smooth. So what should happen is that the derivative as the maximum cannot be negative, okay, because otherwise the maximum was before, okay, you missed already the maximum, okay, it can only be positive or null, and it's positive when you are at the end of the interval, okay. But essentially what this tells you, this is the maximum principle for this linear operator, what this tells you is that you have a bound, okay, because now you look at the right-hand side at that point, and you have a bound which I write in this form, okay, I just factorize the weight in the right way. And you see this is the derivative of the weight you got, and then you put things together. And now I want to choose the weight. You see here I have a singularity because I don't know when this tail star is, so it can be very, very small. So I don't want this in my estimate. I just want to have a uniform bound here. So the right thing to do is that to make the weight compensate for this power of t. And this gives you that you have to take alpha 3 over 2. So this is a bounded quantity. You can take it larger, but that's enough. And when you do this, then you discover that your inequality, what really says is that the supremum of y in the full interval times this function is just bounded by the supremum of the driving term, okay? Independently of the initial condition, because the initial condition disappeared, okay? So this is coming down from infinity, meaning you see that this is becoming small. So if you look this as a bound on y, it's telling you that y is decreasing, okay? So so this implies that yt essentially is bounded by t3/2. Sorry, 1/2. Okay, so independently of the initial condition. Okay, so you have this hard bound, and yt cannot be larger than that. Even if you start very large, then it will come down very fast to match this bound. Okay, so this is the constant depend only on f and on t. If you okay, and you can extend this to parabolic SD. So this is the other way you can get rid of the initial condition, which we didn't want it in our estimates. And this can be extended to the kind of equation we dealt with. Okay, so that's another nice techniques. And I find very interesting to know that, okay, that to know that ODEs can have bounds which are uniform in their initial condition. And somehow the kind of proof I get, of course you can give different proof for that, but this kind of proof, I gave it in this way because then you can do it also for PD, okay, but just using a different space-time weight. Okay. Now let me go to another subject. So I explained to you how to get tightness in the L variable for the measure nu. Now I want to be want to explore other properties of the measure nu. And for example, I want to be able to estimate the average of some exponential function. Okay. So that's my goal. And then there is a method in a recent paper of Steele, which I revisited a bit because it was not stated in this way, but I think this is the core of the method and it will work for us. So the goal is how I use the dynamics to estimate this kind of average. I already told you a way, that is, you use these a priori bounds I showed you. So let me go back. I claimed that somehow you can estimate some exponential functionals, but somehow the kind of estimate you get are not optimal, are not what you expect. So it happened that Irer and Steele recently found a very simple and seemingly optimal argument, which is very nice. So I am explaining it right now. So I want to estimate this quantity using the dynamics again. Okay, so how do I do? Irer Steele do the following. We introduce a new measure, which is just the measure associated with this density. Okay, assume that the function h is bounded. Okay, because as soon as we have the bounds, then we can work with approximation and do essentially the same reasoning. Okay, so I'm aiming at a bound for any function h, let's say bounded, so we don't have a problem to define this quantity. And then later on, I maybe want to put in nice function, but then an approximation argument will work. Okay, and then so what you do? Well, you do that. You know that the integral nu, it's normalized. So the integral of nu is 1, and then you multiply and divide by exponential of h. And you see, you make appear this new measure, and of course you have to normalize appropriately. And then here, since now you have a probability measure, you can use Jensen's inequality for this exponential, and you have a lower bound. Okay, because you are using Jensen inequality for the convex function exponential. Okay, and then you get this bound, and of course now you can divide and multiply. Okay, you can divide multiply by this exponential, the inverse of this exponential, and you get this bound. Did I wrote it correctly? I didn't wrote it correctly. there is an exponential, so I have a bound of this form. Okay, now it's good. Okay, so that's very nice, because somehow I have a bound. This tells me that I have a bound on Z if I can bound the average of H under this new Gibbs measure. But Gibbs measures are not a problem for me, because I know that stochastic quantization can give me an handle on this kind of measures. Okay, so I can consider the stochastic quantization of this new measure. And again, it's similar to the stochastic quantization of the old one. Just remember, okay, so this measure, what is just, let me write, okay, it's just ZH, and then you have the normalization, which come from the other measure, and then you have something like, I had V epsilon, maybe phi, and then you have the Gaussian free field, okay? So this measure can be written as another, okay, it's not different, not very different from the one we already had. Okay, just you have a new energy function, which is this one, and therefore you have to introduce a new stochastic quantization. Okay, and essentially the condition, which I will explain later, somehow is on the function h, is that the function h can be bounded with the good terms we already had, localized, and with any function, any nice function of the Gaussian free field. Essentially, that's why what is this condition. Okay, it's not very important to understand what they are right now, because let me show you how to use them. So again, what I want to do is that now I have a new stochastic quantization equation, because I'm stochastically quantized, not the measure nu, but this new measure rho h. And then I have bounds for that, which essentially are derived in the same way as soon as I can get rid of this function h prime. And then the condition I gave you in the other slide, so namely, these are the condition on the function h I need to be able to do my reasoning, are just the natural condition you would expect. Okay. And then you get your bounds, you use the stationary coupling, a new stationary coupling, but that's not very important. You never rely very much on what is the coupling, just it's stationary. And you get estimates for for your function h. Okay. Again, here I'm not have not been very precise, because again, I've been a bit sloppy because I was confusing Z and H. So let me no, actually, I think I'm because here I have Z while the measure depend on the sum. So let me so this should be X. So sorry, that was my problem. So so what X is the sum of these two. So you see the kind of condition, sorry. So the kind of condition you need is similar also for the function. Okay, you need that when you apply H to a sum of two things, you are able to do more or less the same thing. Let me check what I want to say here. Yes, this is multiplied with phi. Yeah, okay, so something like this. I think yeah, okay, let me be sloppy. I think exercise for you is to find the right condition. Okay, I think here I need to multiply with phi and to sum over the lattice, and then I'm good. And actually withdraw square. Okay, something like this. And here I just need something like this. And that's not very important. And anyway, okay, you need some condition in order to be able to repeat the argument with the bounds, okay, with the function h. But the main point is that is that you get more or less the same argument. So let me cancel this step because it's wrong, but you get essentially with the same kind of argument, you get a bound, okay, because the dependence on weight 0 can be just directly controlled, and the dependence on Z, through the a priori bounds, you convert in some dependence on weight 0. And this tells you that you have a bound for this quantity, which can be expressed essentially in terms of the Gaussian free field, and that's what you wanted. That's why you wanted stochastic quantization. And essentially with this argument, if you are a bit careful, you see that you can prove that you can take a function h as this one, at least on the lattice, but same argument could work in when we remove also the epsilon parameter. Okay, just I want to give you the idea how does it work already in the lattice. So what that's tell you that this family of measure uniformly integrate this functional. Okay, remember rho is a weight which is going to 0 fast enough, and then you can take the L4 norm, because essentially what you can do is to use the L4 norm to control. So essentially you have a L4 norm at your disposal here to control a cubic term here, essentially. Okay, that's somehow the goal. But of course you need a small parameter, otherwise it does not work. Okay, with the L4 norm. If you have a smaller norm here, you can put even a parameter which is not small. Okay, but essentially this is the optimal estimate you expect. Okay, because you see the measure nu decay as the L4 norm, so you expect to be able to integrate the L4 norm. And that was an open problem which has been solved by this paper on iron steel, which essentially used this very simple observation, but it's I find very interesting and very useful. Okay, so my hour, it's almost gone. I think it's, let me maybe spend 10 minutes to discuss some other, let's say we started a bit later, so I have 10 minutes more to discuss, where we are. So far, I showed you two things: how to get tightness out in the parameter L. So how to get the infinite volume limit, the estimate useful in the infinite volume limit. A technique to prove bounds on your measure. Again, only using the dynamics. I'm not using any property of the measure, any detailed property. Of course, I use how the measure looks like, but not estimating directly the measure. Now, what about so we have tightness as I go to infinity. What about uniqueness of the accumulation points? Okay, can I claim that there is a unique accumulation point? Now, you cannot expect this to hold in general, because the kind of measure I'm looking at could have a phase transition, because they essentially like Ising models. And in dimension bigger or equal than 2, they could have a phase transition, which means you could have more than one infinite volume measure. Okay, so there should be some restriction, and an easy restriction to put is somehow some convexity assumption. And I will show you later. I will try to show in 10 minutes how you go on to prove uniqueness using this convexity assumption. Okay, and what you want to do is that you want to compare two solutions. Okay, when you want to prove uniqueness, you say, okay, let me have two accumulation points, which really means two stationary coupling of the Gaussian free field and this field and the solution of the full equation. But you assume that there could be more than one. Okay, in particular, more than one solution of the full equation and more than one measure in the full space. Okay, the family of measure nu epsilon could converge to more than one limits. So I want to prove uniqueness, and the idea essentially is that I want to couple two possible limits. Okay, using the same noise. Okay, because somehow the Gaussian free field is the same in the two limits, so I can just use the same Gaussian free field by conditioning. And then I have a coupling where I have the two solutions and the Gaussian, and driven by a unique Gaussian free field. But the general idea is that let's assume, so let me explain this coupling. So let's just assume that I have two solutions of the shifted equation. So I have y, which is the Gaussian free field, and z, which is the difference of x and y. And they represent somehow two possible infinite volume stochastic quantization. Okay, and I want to prove that, let's say I aim for uniqueness, so I want to take the difference and somehow prove that they are equal, because maybe I choose the same noise for both. Anyway, I want to estimate the difference, so I call h the difference, and then you compute, you do what you know already, you take the difference of the two equations, and you get something like this. It's not very important, the form, okay? It's an exercise to really compute it. The point is that now you proceed as with the a priori estimate, that is, you test your equation. So you have a right-hand side, which you have the difference of the two right-hand side, which you expand in first order in Taylor expansion with the integral remainder. So it's linear in the unknown h, and it's linear also in k, or at least linear in k, where k is the difference of the two Gaussian free field. Think about you're using the same Gaussian free field, so this difference is zero, okay? So you have only h. So you see what you want to do. Essentially, you want to prove that, yeah, somehow you would like to make some kind of Gromwall lemma, and the way to do it is first to test with h with some weight, because I'm in the infinite volume now. So whenever I sum over the volume, I need a weight. So I put a weight, and I sum everything, and then in the right-hand side, if I call q everything, so sorry, this is called q. Yeah, I think I wrote it here. So when I test the right-hand side with h and with the weight, I can do a computation, and essentially, provided I have some convexity of v, which expressed in the fact that the second derivative of v is bounded below, then the idea is that I can bound this with terms which are somehow, they are positive, but they can be controlled with good terms again. Okay, so I have, you see, a second order term in h, which is exactly what I will get as a good term, and a correction term, which depend on k and g, which I consider a perturbation. Okay, so this will be absorbed, and this will be considered a perturbation. And yeah, so how you do, since I'm very fan of testing, I test with this is Gromwall lemma, okay? One way to prove Gromwall, if you want. You test with the growing exponential in time, and this give you a positive quantity like this one, which give you, yeah, so give you this term. And then you see you add these two terms, and you add the Laplacian. So this term was coming from the perturbation. This term is what remains from the perturbation. This is the difference of the Gaussian free field, remember? And then you have, of course, this term, which depends on h, which is your unknown. And you want this term, okay, you have to integrate by part the Laplacian. This already said that when you integrate by part the Laplacian and you have a weight, you get correction terms, okay? This somehow constraint the kind of weight you can put. And for this argument, you are interested to put exponential weights, okay? So if you put an exponential weight, you get a quantity like this, depending on theta square, because I want to take theta large, okay? And you see that theta, so now you can take C large, theta large, so chi is given, this is the convexity of your potential, the mass is given, this is your parameter, all these terms are against you, and this is with you, and you want this to be positive, so the mass has to be large enough in order for this to be positive, and this gives you constraint on theta and on C, and also on the convexity. And then as soon as it's positive, this is a good term, so you can forget about it, this is a good term. and this is the bad term, okay? And now you play the same game. You can forget all the good terms, you integrate your equation, and at the end of the day, you get this inequality, okay? Which is exactly grown one for the stationary measure, sorry. So this is under the stationary measure, okay? So you have something like this. Okay, so again, remind that this H is the difference of the two solutions. Okay, so you don't know very much about it. So you cannot say anything about this. You can just bound it. But you see that here you have this exponential. So when you send t to infinity, this will disappear. And this will tell you that, okay, this will disappear if you're using the same noise, so k is 0, so this disappears in the infinite, in the limit t goes to infinity. Anyway, you are stationary, so this does not depend on t. This disappears because k is 0, because you choose you coupled the two solutions in such a way that the Gaussian free field are the same. So this gives you uniqueness. Okay, so I noted it here. And you can use it also to get other information, okay? For example, if you really use two different noise, but the two noise are the same in a very large region, then somehow this quantity can be made very small, because this is 0 when in the large region, and outside the weight is small, and it's exponentially so. So this is exponentially small, for example. And this tells you that inside the region, for example, the two solutions are exponentially nearby. Okay, so you can modify this kind of idea to obtain, via stochastic quantization, decay of correlation. And this is work in progress. We have a paper finished soon, I hope, with Hoffmanov and Dran about controlling decay of correlation in stochastic quantization. Okay, so I think it's a good point to stop, because then I want to talk about the small scale limit. So this I can discuss next time. Maybe I will not go very far, but I think it's a good point. So let me summarize a bit what we did. What are the interesting points to me of what we did, okay, apart from the technicalities, okay? But all we try to do is to express the interacting field, so the full solution, the process which has our interesting measure as an invariant measure, as a function of the dynamic Gaussian free field. Okay, so this is my stochastic analysis. And then you see that the interesting measure becomes just a functional of the measure of the dynamic Gaussian free field. Okay, you give me the Gaussian free field, I solve this complicated nonlinear PDE, or actually this is the equation, and I get information about, I get the measure nu, and I get information about the measure nu. And then there are really two different steps. You do probabilistic estimate of the Gaussian free field, and you do pathwise analytic estimate on the map F. Okay, and if you think about it, many instances of, even in stochastic analysis, many kind of results you can get on diffusion is a mix of probabilistic and analytic estimates in the same spirit. Okay, so that's why I try to think about this method as a stochastic analysis. And what plays an important role is the coupling between the full solution, X, even with the dynamics, and the Gaussian free field, Y. So out of this stochastic quantization method, there is always this benefit you get, that is, you don't only have a measure nu, you have a full coupling between this measure and the Gaussian free field. Okay, you have a way to go from one to the other. And already this is interesting in the infinite volume limit, because as soon as you took the infinite volume limit, the measure nu is not anymore absolutely continuous with respect to the Gaussian free field. Okay, while in finite volume and on the lattice, the measure nu is absolutely continuous, and we define it as with a density. As soon as you take the infinite volume limit, the two measures are not anymore absolutely continuous, but still you have this coupling. Okay, so you can use the coupling for studying the measure. And as we will take the epsilon going to zero limit in dimension 3, the measure even on a finite volume would not be absolutely continuous. Okay, so so the random field so the random, so the idea somehow, yeah, actually in the large scale is not very meaningful. So let me say, so the idea then, not only the coupling relates the interacting field with the Gaussian free field, but somehow what remains, it's very nice. And we will show tomorrow in which sense it's very nice, especially when you take the epsilon going to zero limit, you will see that somehow the very irregular part of the random field X is encoded by Y, and Z it's more regular. And this is a key to have renormalization going on. Okay, so tomorrow we'll discuss renormalization, at least in 2 dimension, and yeah, maybe some related results. Okay, so for the moment I stop here. Are there any questions?
Thank you, Massimiliano. So I will stop the recording, and if there are any questions,